feel free to unmute your camera and your microphone as well. So the first question talks about the difference with one RMA approach. It says that prior solutions such as one RMA promise high scalability. And what are the differences between these two?
Yeah, can you hear me?
I can hear you, but I can't see you, Sumit.
I have enabled video, so let me give another try.
Okay. Yes, perfect.
Yeah.
So,
yeah.
So you heard the question?
Yeah. So yeah, the primary difference between Flock and one RMA is that one RMA re-architects the RDMA NIC, the NIC itself. So the NIC is itself connection free. So the whole idea of one RMA is kind of different from our thing is mainly with vanilla RDMA hardware. So how we can improve the scalability. So that is up to a point because connections are inherently non-scalable, but how we can improve that is our motivation. On the other hand, one RMA changes the NIC itself so that you can have solicitation for data transfers. So that is the primary difference.
Got it. Thank you. There is Edward, your hand's up. All right, go ahead.
I also started to, I noticed that someone had asked basically the same question in Slack. Hugo was asking, what if one of the threads, which is sharing the same message buffer in the leader follower set, is slow to complete and doesn't fill the buffer promptly? Does this hold up other threads that are sharing the same buffer?
Yes. So if one of the threads is slow, then we have a, so in that case, you can consider that it becomes a flat combining approach where the leader can actually complete the work of the follower. So if there is like a long delay, then the leader can itself do the thing.
So, will the leader then send the message without the follower's data if it sort of runs out of time?
Yeah, so actually when the follower actually submits the request actually contains the pointers to the data and metadata. So it's like, who does it first? If the leader wants to do it, it can do it.
Oh, you made it look like the leader handed out a pointer to the buffer and then it was up to the follower to put its data into the buffer. And
yeah,
then you wonder, well, what if the follower just stalls and doesn't put its data in?
Yeah.
Okay, that makes more sense.
Awesome, awesome. There's actually a follow-up question to that, Sumit. Joel Nider is asking, how is colisting affected by a mix of latency sensitive and throughput oriented workloads?
Okay, so in terms of addressing that, so our goal with the sender side thread scheduling is basically to address this thing in a manner where, so when we do coalescing, so when multiple threads are sharing a queue pair, our primary goal is to avoid head of line blocking. So by latency sensitive, I am assuming the threads which are submitting small payloads, while the throughput oriented are ones which are sending larger payloads. So we try to place the threads on queue pairs in such a manner that the threads that are sending smaller payload are grouped together and the ones sending larger are separated so that there is no head of line blocking and you can have a good balance between the throughput and latency oriented applications.
Well, thank you so much. There is just one follow-up question from Hugo. It says, I was also wondering why the throughput keeps increasing with increasing number of threads, even when you have more threads than cores. If the benefit is coming from coalescing, would reducing the number of queue pairs in the client improve your throughput?
Yes, so what we have at the server side is we limit the maximum queue pair count. So as the number of threads increases, the number of as the number of threads per client increases, the coalescing degree increases, because one thing is constant, which is the maximum queue pair count. And if there are a large number of threads which are grouped on smaller number of queue pairs, then the coalescing degree increases. A coalesced message will have more number of requests. As a result, what happens is each coalesced message will have more number of requests. That kind of efficiently utilizes the network because the ratio of data to metadata increases, where the data is the actual payload and metadata is the network transport information headers. So if you are sending like 64 bytes and you have for every 64 byte, you have like, let's say 36 byte header, then you are wasting a lot of information. The data to metadata ratio is small. But when we coalesce and the coalescing degree increases, the network is efficiently utilized. So you have one header for multiple requests.
Got it, got it. Perhaps last question in for just 2 minutes before the next talk. There is a follow-up question of using credits to manage load on the server. As the credits for the client threads using up more bandwidth, that's more traffic, are the credits for the client threads use up more bandwidth with more traffic taken away? Or the ones that use less, could you please elaborate a bit more about the fairness across threads?
Yeah, so the clients that have been more active. So our criteria for deciding as in how much to allocate to how the server decides the number of queue pairs or the credits for each client is based on what is the utilization metric for each client. So if a client is very active, then we kind of reward it in the appropriate proportion. So if the client is sending more requests, then it gets more credits. And similarly, if there is more coalescing from a client side, that means more threads are sharing queue pair, which is like higher contention on a single queue pair. So we kind of reward that to balance both things, the utilization and the contention on the queue pair.
Got it, got it. Thank you so much, Sumit. Very interesting work. Feel free to answer questions on Slack offline as well.
Sure, thank you.
Okay, thanks everyone. Before moving to the next talk, I'm going to hand in chairing this session to my vice chair, Jijun Jung. Please stick around. There's still another talk, and we're also going to have the panel discussion. Jijun, take it away.
Okay. Yeah, thanks, Monia. So I'm Zhizhen Zhong. I'm a postdoc here at MIT with Monia Gobadi, and I work on system and networks. So let's move on to the third talk of.
I'm Sumit. So Sumit, if you can unmute and turn on your camera. And once again, we have, oh, now I'm getting an echo. Once again, we have no questions in Slack. If someone would like to raise their hands and I can figure out how to spot whose hands are up, or if maybe VJ can do that for me. Sumit, are you here?
Yes, okay. I can hear you.
Okay,
but I cannot start my video.
Okay, let me see where I can.
The host has stopped it.
I think somebody fixed that for you, so you should be able to turn on your camera now.
No.
Oh, well, it's not that important. So does anybody have a question they want to ask in Zoom? If not, and again, I'm not sure how to find the, oh, there you are. Okay, now you can put your camera on. I'm not sure how to see the hands up, but I didn't see anybody. So we have a few prepared questions. So first one is for the RDMA NICs, can you conceive of any hardware features that might make it easier for you to do connection sharing?
Yeah, but again, you can, but again, it depends on the application, and you can have a naive sharing mechanism, but it depends, because when sharing, you don't want to have head of line blocking in terms of a smaller request getting behind a larger request. Mm-hmm. So if you have something in hardware, then that is like a fixed function. So you cannot change that. If something is behind a larger request, a small request is behind a large request, then it is difficult to, as in you can't solve the problem then.
Well, you know, something that might give you more visibility into what queues are in hardware. I don't know whether that would be helpful or not.
That can be, but something like a sharing mechanism in hardware, I think that will be.
Yeah, it might not be a full sharing mechanism. It might be something to make it easier for you to implement your server. Okay. Another question. Can you apply flock to threads that don't share an address space or a process? I mean, how much sharing do you require on the client side, I guess?
Yes. So in this work, we primarily focused on multi-threaded applications. So multiple applications or multi-tenancy support is kind of like a future work. So, but there is a possibility to do that by sharing memory across processes. But we deliberately did not, as in, took that option. So our scope is limited in this work.
Okay, we now have a question in Slack from Yo-Yo Lu, and the question is short. Thanks for your talk. I'm wondering how to compact messages with different sizes of different threads to a single buffer. Is there any overhead? I'm not sure I understand the question, but maybe you do.
Different sizes. So in Flux, our categorization of threads into different sizes is, so we basically monitor the request sizes of each thread as in over a scheduling interval. So similar sized requests are can be placed together on a single queue pair, and given that these similar sizes are small, so that you can actually take the advantage of coalescing. As in, coalescing is only beneficial when your data to metadata ratio is small. For large messages, coalescing is of no benefit. So our goal is to actually monitor what is the typical or median request size per thread and decide to place them, multiplex them among the queue pairs in such a way that it eventually benefits the coalescing.
Okay, thank you. Now we have another question in Zoom from Inho.
Yes. Hello, Sumit. Thanks for the great talk. I'm from NUS. Yeah. So I have a short question about the credit in your work. So I understood that the purpose of the credit is to kind of balance the load from the server side. Yeah. But could you elaborate a bit more the purpose of the credit in your work? Why you use the credit thing in your system?
Yeah, so the credit scheme is basically similar to like other transports which are primarily receiver driven, like HOMA and phost. So what we want to do with that kind of a scheme is we want to control, the receiver should be able to control the load that it has to handle, the number of buffers it has to poll, and the cache thrashing it has to prevent. All of these things the receiver has to control. So what we want is the sender can only send if the receiver has provided a credit. So this basically allows us to control. So by doing that, we can monitor the activity of each of the client. The clients which are more active get a higher portion of queue pairs, and the ones which are less active get a less portion. Another thing we check is the queue pair contention, as in if there is a high coalescing happening on a queue pair, that basically indicates that multiple threads on that queue pair are concurrently submitting requests. So that is a metric, that is a contention metric that we use. So higher contention, then we try to provide more queue pairs so that they can separately send their requests.
I see. Okay. Yeah, thanks. Yeah.
Thank you for your question.
Okay, I don't see any other questions in Slack or Zoom. Again, my Zoom skills are pretty limited, but I think we're getting pretty close to back on time. So why don't we just move on to the final paper of the session, which is, and thank you, by the way, Sumit. The final paper is PRISM, Rethinking the RDMA Interface for Distributed Systems.